guess I'll start now. Hi everyone, my name is Mihir. I'm from the Mycelium research team, and we're predominantly based in Brisbane, Australia. And we're just quickly going to be showcasing the work we've done over the last few months. And before I get into all of that, I'll just be explaining briefly why we want to build likelines for the consensus layer Ethereum. So basically, last year in November, I read this article on CoinMarketCap. It was written by Matt Garnett. I'm sure some of you know him. He's a core developer for Ethereum. And in his article, he mentions that Ethereum has a few centralization points. These are basically, these dApp developers, they've been using node services like Infura into the applications, and there's also, we have wallets like MetaMask. They use Infura by default. And also some of the rollups as well, like Starknet nodes, they use Infura as well to sync with them, to interact with the Ethereum network. And yeah, this article really opened my eyes as to how big of a problem this is. And the reason why this is happening is because there's only one way to interact with Ethereum, which is by running your own full node. But that itself is very difficult for most users because it requires an understanding of command prompts, typing these commands, troubleshooting these errors, setting it up. It could be quite, you need some sort of developer experience to interact. And so that's a very bad user experience, and there's also financial costs as well. If you want to sync from the sync and get node, it takes a very long time because the state size is over 100 gigabytes. And yeah, and what has happened is node services like Infura, they've removed these barriers, and they've just provided a straightforward API that you can use in your application, and you can start interacting with Ethereum. And you saw this is why they've been growing. So the long-term, so if we don't have multiple implementations of likelines, and we don't have efforts like Portal Network, I think we will eventually start seeing more and more cases where users who cannot afford to run a full node, but if they're relying on services like Infura to interact, they'll be locked out. And locked out is in they won't be able to interact with Ethereum. And one example was this year in March, basically Venezuelans were unable to interact with Ethereum because they were using Infura. And what happened was Infura is a US-based service, and they have to operate within the rules and regulations of the country. And so they cannot really provide the services to countries that are on sanctions. And basically some misconfiguration happened on their behalf, and that led to some downtime. And so users were basically locked out. But I just want to say one thing. I'm not condemning Infura or any node service. I think they're really great. And they're really great that they provide infrastructure to Ethereum. And they could be great for testing, for if you want to test your smart contract application on a test network, like Rinkeby, you could just use that. That's going to be fine. But it would be great if it'd be great to have alternatives for if people who cannot run a full node, but if you want to interact with mainnet applications. And yeah. So we want to address this. We want to build a production-based likeline for Ethereum for the consensus layer, and that is able to run in resource-constrained environments like the browser as an extension, or mobile phones, and then eventually IoT devices like smartwatches. And it's obvious the reason we picked these three is because these are highly accessible ways to interact with the internet today. Like for example, in the browser, you could just type the URL, and the web page just loads instantly. Mobile phones, they're really portable, and you just click on an app and the app loads. And smartwatches are even more portable. So that's basically our target that we want to create a likeline for. So the progress so far we made is back in February. So this year February we created a prototype likeline in C#, and it implements the sync protocol specification. And basically it has two functionalities at the moment. It can sync to the latest block in the beacon chain, and it can verify information from the beacon state object. It can verify the Merkle proofs. And we also, around March when, yeah, around March. So we also worked on like a experimental implementation of a lib peer-to-peer routes defined in the draft GitHub pull request. Yeah, and what happened was so the status team, they deployed some nodes on the Kiln merge testnet that could serve like-line data over lib peer-to-peer. And I used the ENRs they gave me to connect with those nodes and get the data over lib peer-to-peer, and it worked. But the thing was, the Kiln merge testnet has a lot of other nodes as well, like from Prism, Lodestar, all the client teams that don't yet serve like-line data over lib peer-to-peer. So discovery was the only issue I had, but yeah, it's expected. Like there's only, yeah. So I guess I'll explain now how quickly how consensus layer like-lines work. So you basically need two things: a full beacon node that can serve like-line data, and you need a checkpoint route. And the full beacon node you can run locally on the same machine the like-line is running on, or you can run on a different machine. What you're really interested in is in the API endpoint of that beacon node, and then the like-line use that API endpoint to get data to sync with the network. And as for the checkpoint route is just a block route that you can get from a variety of sources, like the block explorer, your friend's node, or if you're running your own node, you can just use that. So once you have those two things, you provide it to the like-line, and basically the like-line sends a request to the full node through the API endpoint, and the checkpoint route you provide, it requests a snapshot. The beacon node returns a snapshot containing the block header at that checkpoint route, and the sync committee that signed that block header, and the proof of that sync committee. So we only verify if the checkpoint is a valid starting point to sync with the network. And then once we verify that information, we request a range of sync committee updates. Now, the checkpoint route, because the sync committee changes every 27 hours, and the checkpoint route could be, it depends, it could be multiple days old. So in order to get, and the sync committee would have changed multiple times. And so in order to get to the current sync committee, we would request a range of committee updates. And yeah, you verify those range of updates, how the sync committee changed by looking at the proofs in the beacon state. And once you verify all those range of updates, you basically request you poll every 12 seconds the full node for a new header. And because every 12 seconds a new block is added to the beacon chain. So in order to keep track of the latest state route, you request the header every 12 seconds. And yeah, I'll just quickly show you the demo. So, so this is the C# implementation. It's the user interface. And as I mentioned earlier, it needs two things. It needs a API endpoint. So I'll just have it here on the notepad. And needs a checkpoint route. Now, I'll be using the Beacon Chain Explorer to get checkpoint route. So we can just use, I'll just refresh that. We could just go to this one of the recent epochs, and we can pick any block route from the Explorer. Copy that. And so the like-line quickly synced with the latest block in the beacon chain, but we're always one block behind because the sync committee always signs the block previous than the current one. And so, yeah, this is the interface. And the only utility this like-line has right now is you can query the balance of validators. Yeah, and but I'll just type in a random validator index from the beacon chain. And this is getting data from the mainnet as well. So, okay, so when the progress bar reaches the end, we'll get the balance of the latest validator. And we're verifying this balance by checking the multiple proof that we get from the request. And so we verify the proof against the state route we're keeping track of here. And the state route changes every 12 seconds. And so we have to request a proof every 12 seconds. And yeah, that's basically the utility it has, I just want to say it's not really like beacon state object has many other fields like finality checkpoints, latest header, genesis time. You can request all that. It's not just restricted to validator balances. And what's really exciting is like post merge, you'll be able to like post merge. They'll be adding a new field, execution payload header, and you can use that, for example, to verify if your transaction was. You can get some assurance that your transaction was included in the future block. So if you send a transaction to the execution layer, and you want some assurance that your transaction was it included or not, and you can use the light client to quickly sync with the network and get some confirmation. And we can verify this confirmation through we can request proofs for that whether the transaction was included or not. And yeah, that's basically the demo. That was the pre-recorded if something went wrong. So what's next for us? Well, okay, so we tried with the lib peer-to-peer approach. There are a few challenges. Now, lib peer-to-peer library exists in only 3 languages at the moment. It exists in Golang, Rust, and Node.js. There were attempts by many developers to bring this library on C#, but the thing was, it was too big of a challenge, to bring this lib peer-to-peer library for one person, because lib peer-to-peer library is quite complex. It has a lot of moving parts to it, and so you need a full team dedicated to this effort. And the only thing, it makes sense, so in order to make it work in C#, the only logical thing to do is just have the lib peer-to-peer instance running, and then you have the C# instance running, and then have some communication through the APIs between those two, and just package this together in order to make it work in resource-constrained environments. And one thing I'm really excited for is when Portal Network is active, when all the networks are active, we would like to use the transaction gossip network for allowing the light client to send transaction to the execution layer, and then those transactions could be processed. And in order to make that work, we will probably need to implement some libraries in C#, and then start building Portal client implementations on that in order to make this work. And obviously, also with the state network as well, we could request execution layer data, like reading contract balances. That's very exciting. And yeah, that's pretty much it for me. Thank you. Yeah.